The models that SYMMIC analyzes are described in device template files. And let's take a look at a couple of examples, starting with the mesa resistor. The mesa resistor models a rectangular heat source in an integrated circuit. Now, the template contains all the information necessary for performing a thermal analysis. The aspects of this information that the user can modify are described in a help file, which can be viewed by selecting Device Template from the Help menu. The help file shows the geometrical parameters, the dimensions that can be modified. It shows the names of the components, in this case, for example, the components in the stack up, and gives a description of these. And if we go to the device menu, we can see there are lists here, and if we open one of these lists, for example the geometry list, here we have a list of the parameters described in the help file. And if we want to modify one of these, we can double click on it, type in a new value, and the model is immediately updated to reflect this change. The thicknesses are the parameters for the thicknesses in the stack up, and we can modify those in the same way. So if we want to modify the thickness of the mesa, for example, we would go in and type in a new value, and the model would be updated to reflect that. If we want to change the materials that are used in the stack up, we can go to the components menu, and here this lists all the components in the device and the materials that are currently assigned to those components. So if we wanted to change the substrate material, for example, we would double click on the substrate, which opens this dialog, and then we just open this pull down list until we find the new material that we want to use. Click on it and say OK, and the model's immediately updated to use this new material. If we want to create our own material, we would open the materials list, which shows all the materials defined in the template file. And at the bottom there's an entry that says add, and we would double click on that, and then we type in a new material name and a new description, and we could assign a color to the material, and then we enter any physical properties we have. For example, thermal conductivity. If we know it's thermal conductivity at different temperatures in degrees Kelvin, we would enter the temperature, and then in this next column we would type in the conductivity. So let's say it's 10 watts per meter Kelvin. That would be 10 to the minus e to the minus 6 watts per micron degree Kelvin. And since it's isotropic, we don't need to enter values for all three directions. And once we're done entering properties, we say OK. And we scroll down, we see that our new material is added to the materials list, and if we double click on it, we can see its properties, and we could go in here and change these or add the specific heat capacity or mass density properties, whatever we have. If we want to use the new material, we go back to the components list, select the component that we want to apply the material to. Let's say the backside adhesive. And we'd scroll down till we find our new material, and we say OK, and it's just that easy to add a material and use it in the model. So let's go back to the help file. In addition to the components and the geometric dimensions, we also have information on the boundary conditions. The cooling in this device is defined as through a backside film boundary condition. So you have parameters that you can specify for the temperature and the heat transfer coefficient for the film. The heating or the heat power dissipation in this device is a uniform volume flux distributed throughout the mesa, and again you would have a power parameter, an on power parameter that would allow you to change that. So if we go back to the device menu and we look at the heat generation parameter list, here we see the backside film coefficient and temperature parameters, which we could change, and the on power parameter, which is the power applied in steady state, and then there are additional parameters here for transient simulations when you're applying pulse power. We won't go into those, but let's take a look at another example template, the generic FET template. So we'll open that file. And now the generic FET template models half of a symmetric field effect transistor. We only have to model half of it because it's symmetrical. And again, we have in the device menu a list of a lot of parameters. And if we go to the help file for this device, we see a description of the device. We see labeling of the numbering of the drains and sources for the device. And we see a picture showing all the components and their names, and a description of the layers and what they are. Then this picture shows all the geometrical dimensions on the top of the device that we can modify. And since there's a lot of these are grouped into lists. So we have source lengths, drain lengths, pad bus boundary dimensions, finger channel gate dimensions, and this image shows a cutaway at the top of the substrate, and you can see the via holes from this top view and their dimensions. And again, those are described in another list. So if we went back to the device menu, we'd see basically each of these lists: the source lengths, drain lengths, via holes, finger channel gate dimensions. And if we open up one of these lists and double click on a particular dimension, we can go in and type in a new value. In this case, the finger width. I'm doubling the value of the finger width, so immediately the model's updated to reflect that. So we can basically stretch and modify this this device to match any particular device that we have, any particular geometry. In terms of the heat generation parameters, if we scroll down in the help file, we find a description with a picture here of the boundary conditions. Again, we have a backside film boundary condition for cooling on the backside. For power dissipation in this FET device, what we have is heat generation in a very thin layer between epilayer 2 and epilayer 3. All along the channel from the bottom of the gate to the edge of the drain. And we have additional control over how power is dissipated along that heat dissipation region by these parameters, which describe a set of 4 segments. We can specify the widths of these segments, and then we can specify what percent of the total on power is applied in each segment. So if we go back to the device list and pull up the heat generation parameters list, what we see is the ability to specify the widths of those 4 segments and the percent power on each of those 4 segments, as well as the backside film parameters and the on power and pulse power parameters. So one final bit of information that's available in the help file is the meshing refinement parameter. It's one parameter that lets you actually increase the number of mesh elements that are generated for the simulation. By default, the default value uses an optimal mesh that's optimized for accuracy and speed. If you increase this parameter, though, you can increase the number of mesh elements and basically verify that the meshing is reasonably accurate. And then the final item in the help file is the description of the layout characteristics for the device, which basically describes how the device will behave when you incorporate it into